I feel like it's like one of the worst areas.
All right. Let's talk about today's lab. So, where are you? What chapter are you on in your course?
We just finished 7 and 8 theoretically.
We're on unit 2, so right now we're on chapters momentum of inertia and angular momentum activity.
Have you done centripetal motion?
So that's chapter 8.
That's chapter 8.
And that homework's due today.
Yeah, that works here today.
Yeah, that's one.
I don't know when it.
So you've already done it. That's what I'm hearing.
No.
Because people
No, we have not.
I didn't even.
waiting to the last minute. What?
Well,
We didn't even
have the work available to us
Yeah.
till like literally the other day.
Thursday, and then he had stuff, or whoever had stuff due on Easter, and we had stuff due today.
Yeah.
Yeah, and it took me 2 days to get through chapter 7 notes without the PowerPoint notes because it's so long and there's so much, and
There's a lot.
there is a lot. And I mean,
It was supposed to be released like 2 weeks ago. That's what I was telling you about.
Yeah,
the last.
yeah. And
Yeah.
Ms. Sasson opened it up. All right. Well,
some notes on rotational motion and linear and angulars, but I don't understand anything.
all right. So let's hit a couple points here. Acceleration. Doesn't do a whole lot. Come on. You can do it. There we go. All right, acceleration. What is acceleration? It's the math definition.
It's the change in velocity.
You started trailing off there. Say it like you mean it, whether you're right or not. Just say it
Is
with
it
confidence.
the change in velocity over change in time?
Yes, it is.
Huh. Or displacement?
All right. That is acceleration. What is velocity? We'll be going to the conceptual definition
Change
this
in
time.
position over change in time?
That is true.
Or that average change, displacement over change in time?
It seems like you threw average in there in a strange spot.
The average change in position over change in time is what the average velocity is, right?
The average velocity is change in position over change in time. It's not average change in
Oh.
position. You're close.
Thank you.
What's another definition of velocity?
Like a word or equation or?
Or words, not looking for the math. I suspect that what I'm looking for is, you all know, you're just trying to do what is he trying to, you're trying to think about what is he thinking as opposed to what velocity is. How would you have defined velocity before you took the course?
Miles per hour.
Okay, so we got units. So what's the relationship between velocity and speed?
Speed is in meters per second.
Okay,
Velocity is in meters over seconds.
no, it's still meters per second.
Well, speed doesn't show direction, it's just.
So it's the scalar of it,
Right, so speed is the scalar,
and velocity is the vector.
like you mean it.
Velocity is the vector.
That's like you mean it. Okay,
It's 9 a.m. Give me another 2 minutes.
all right, yes. Velocity is a vector. What does that mean?
It means it takes in 2 different considerations, so it's not just it's like direction and force,
Okay. Whoa,
or magnitude.
yeah, thank you. All right, so what I was going for, the mind reading skills, which apparently you do not have at this point, velocity is just speed in a particular direction. So I have a change in velocity if I change speed or if I change direction. probably asked before, what are the 3 accelerators in a car if you're driving?
The gas pedal, the steering wheel, and the brakes.
Yeah, all right. So in chapter 3, you dealt with acceleration primarily from change in speed. In chapter 8, we now deal with acceleration because of change in direction. So if you're going around a curve, you're initially going in that direction, then you're going in that direction. There is a change in direction. Even if you put it on cruise control, a really good cruise control where you're actually going a constant speed, there's still acceleration going on. Because Newton's first law, an object wants to keep doing whatever it's doing. If there were no force acting on you, you would just keep going that way. But I think most of us who've driven have gone around a curve at some point. Potentially people in, let's say, Kansas, I guess, or Utah, where you could fall asleep. If you have got good alignment on your car, you probably could fall asleep and still not get off the road. So if my direction changes, so change in direction means that I have a change in velocity, which means that I have an acceleration, which means therefore there is a force. In this particular case, well, your car wants to go this way, but you end up going this way. There's something pulling you this way. We could even go for, the usual stunning visual effects. Ooh. There's a force that is pulling you in. Every time you try to go out, something just keeps pulling you back in. Use a Godfather 3 reference. This force that is pulling you in right here, this is the centripetal force.
It's an E at the end, is it T-E-L or T-A-L?
T-A-L. Are you mocking my handwriting?
No, I'm just clarifying.
Okay. Either way.
Maybe not.
And for those who can't decipher. Centra meaning center, and pedal meaning seeking. So this is center seeking. It's not the other one, the one that's usually used. I'll write it over here, and then potentially you'll never speak of it again. This is something different. It's related to it, but it's different. This is center fleeing. So this would be something that's going away from the center. Centripetal is something going towards the center. This is usually misused, and you probably are okay never using it in Physics 110, or Physics 151, or Physics 251, or it takes a while before you get to the point where you can start to use this with some knowledge, maybe senior year. But this is usually misused, and so therefore you probably should not speak of it. It feels like you are moving to the outside of the car, but in fact, as you are going around the curve, so if I'm going around the curve this way, it feels like I'm moving towards the outside, but really my body wants to go straight and the car is pushing me inwards. And then the road is pushing the car inwards. Usually if the road is flat, through friction mainly. And it turns out that this acceleration here, the magnitude of this centripetal acceleration, this shorthand for magnitude, is equal to how fast you're going squared divided by the radius of curvature. In other words, how tight of a turn you're doing. So if you're doing a really tight turn, so R is small, you're more apt to skid. Let's say you're going 50 miles per hour down the road, you're about to turn onto a side road, you do a quick, almost right angle turn. There's a really tight radius, you're much more apt to skid because it's a lot harder to do this. The friction is not enough. Also, the faster you're going, the harder it is. So if R is small or V is big, in order to make the current turn, you need a bigger centripetal acceleration. which means you need a bigger force, but there's only so much force the world is going to give you. In this lab, we are playing around with this formula here, is that we are going to be swinging the stopper around. Now, when you do the lab, you're not holding onto it down here, maybe just to get it started. Let's tack on a mass to it. Now, if I just let go, that stopper just will start moving. I can't keep it in equilibrium because this mass is significantly larger than this one. However, if I swing it, this will be in somewhat equilibrium. So the weight of this should be equal to the tension in the string, and the tension in the string is what's keeping this mass from going in a circle. So you're going to measure the mass of the stopper. Triple beam balances, that's what I left off. And I don't even have it in the apparatus here. That's an issue. Okay. I'll get some triple beam balances. You're going to find the mass of the stopper, and then you are going to ignore whatever you're measuring. You're going to write it down, and then you will not use that mass again until the very end. But you'll need to know it to see how good your results are. You're going to swing the stopper around. You're going to time how long it takes to go around 20 times. And then you'll know the speed of the stopper, because the speed is going to be, well, it's traveling in a circle. It's an overhead view. You'll know this radius here. What's the distance around?
Circumference.
Which, and the formula?
Pi equals r squared.
The other one.
Pi equals.
You're putting equals in the wrong spot, but pi r squared is the area. Circumference?
You're expecting a lot out of me this early. I'm trying.
I'm very big. All right, 2 pi r. Over the time. Well, actually, what you're going to do is you're going to measure 20 swings, then you're going to find the average time. Make sure I worded it that way. There are several different variations of this same thing here. Yeah, you'll find the average total time, then you'll find the time for one revolution. And when you're talking about repetitive motion and the time it takes for it to happen once, generally use a capital T, and this stands for period. I don't call it period here, but I do use the capital T, time for one revolution. And so your speed is just going to be the distance it travels divided by time. And then your speed squared is whatever number you get there, squared. You're going to do a plot, linear speed squared versus centripetal force. So we do speed squared versus the centripetal force. Now the centripetal force, if I do a side view, this thing's going around in a circle here. You're going to have the tube. I'm going to have some hanging mass down here, which I'll label M sub H. Then I'll have 2 forces on it. It's going to have its weight, the hanging weight, and tension. Over here, I'm going to have tension acting this way. The tension is the centripetal force. So the tension that you're plotting over there is just going to be equal to the hanging weight. So that's mass, the hanging mass times G. And for this lab, I did not specify, so 9.8 is fine. Meters per second squared. Questions up to here? Now, how good a result should you expect? I like the lab, they're not great results usually. 25% error, it's okay. If you're 100% off, I will suspect that you've made a math error somewhere. So just keep that in mind when you get results. Okay. One thing to note is that the more mass you have hanging on the bottom, the greater the centripetal force. The greater the centripetal force means you have to swing it faster, which means the times should get smaller. The faster you're going, the less time it takes to go around. So, as you're doing this, we can't get a frictionless situation, so there's going to be some variation here. But as the mass increases, you should be getting smaller times. If you get an average time that's greater than some, if it seems off, redo the trial. Also, the mechanics. The hanging mass that you start with on the bottom there has to be bigger than the mass of the stopper. So if you happen to get a stopper that's more than 50 grams, then make sure you're starting out with more than 50 grams here. When swinging it, sometimes it gets a little bit off and you're seeing something like this. You want it as horizontal as possible. Now, potentially it can be corrected. There was one situation, actually two situations, in which a person was having difficulty swinging it horizontally, and I thought, oh, let's try something different. How about swinging it the other way? The person was swinging it the other way, and it was really nicely horizontal. So if you're having trouble making it horizontal, try swinging it the other direction. Whoever is swinging it, there's a good chance you're going to hit yourself in the head with a stopper. Just be aware. It's sort of awkward when you sort of, what I'll call dismount, and when you want to stop swinging it. Sometimes there's this maneuver right here, or sometimes it'll just hit you in the head. No one's got the big bun on top of the head, so we don't have to worry about that issue. But if you have Tyrannosaurus Rex arms, you might not be the good person to swing it. I don't think anyone in here has that, but I guess we'll find out. And I will acknowledge, if you watched the video I did for this, for the 151, 251 version of it, I do not swing it horizontally at all. I need to reshoot it. But I was having all sorts of issues. I think with that, the people who are not here, any idea if they're coming in?
Not my group, they're not.
Heather's not coming in. She has something going on with her hand or something.
Okay. I'm thinking a group of 4 and a group of 3. Let the rejoicing begin, because as you know, it's physics.